Okay, thank you, Professor James, for introducing me, and good morning, everyone. I'm Tomáš Vojtek from the Brno University of Technology in the Czech Republic, and I'm going to talk about intrinsic behavior of Mode 2 and Mode 3 fatigue cracks in metallic materials. And more specifically, we deal with long fatigue cracks loaded in the near threshold regime. And at the beginning, I'd like to say that the crack fronts are microscopically tortuous, and they are loaded by a local mixed mode 1+2+3, which is also true for the pure Mode 2 and Mode 3 cracks. And dealing with shear mode cracks, there are some difficulties because we have the interaction of fracture surfaces. So we have a high amount of crack tip shielding, as well as induction of additional Mode 1 loading of the crack tip. And we are interested in the intrinsic behavior and measurement of the effective thresholds. So we suppressed the crack closure using the cyclic compression pre-cracking technique. And using this technique, we obtained open pre-cracks generated under compression under Mode 1. And here is an example of such an open pre-crack. And in this case, when we apply Mode 2 or Mode 3 loading, we don't have contact of fracture surfaces, and we are able to measure the effective thresholds, which is a value that it is between the case when we observe no crack propagation and at least some crack extension. And using this, we found different initial crack propagation direction in different metallic materials. So it could be a coplanar propagation within the pre-crack plane, or branching towards the local Mode 1 crack growth, or in different materials it can be some combination of these two limiting cases, 1 or 2. So for the purpose of quantitative description of Mode 2 effective thresholds, we divided the materials into two groups, where the crack growth is controlled by the local Mode 1 mechanism and local Mode 2 mechanism. And no local Mode 3 growth mechanism was revealed. So this is what classical energetical criteria for mixed mode crack propagation do not take into account. Here, for a remote Mode 2 loaded crack, we investigated the case when the crack front is deflected by the angle alpha, and we determined the local stress intensity factors in Mode 1 and 2 by the widely used equations. And then we substituted these local components by effective thresholds for ideal cracks, and in this case we could obtain the values of the remote Mode 2 effective thresholds, determined for the case that the crack growth is controlled by local Mode 1 or local Mode 2. And here, to evaluate these equations, we need to know the deflection angle alpha, which we measured for each material. And we use this method, stereophotogrammetry in scanning electron microscope, where we were able to measure the third dimension of the fracture surface. And here is an example of a crack growing under Mode 2 from niobium. And we could observe two things. First, we could measure the crack propagation direction, so it means the deflection angle. We measured this on several pictures for several specimens, and then we obtained some characteristic average angle for each material. And second, when we look at this profile perpendicular to the growth direction, you can see here, and we found that actually these lines are parallel to the local crack propagation direction, and they originate on local irregularities of the pre-crack front in 3 dimensions. So this is important for the next analysis of mode 3 cracks. And so based on this analysis, we were able to formulate a guideline for various metallic materials with different structures. And here are the characteristic deflection angles for the materials, and the appropriate local mode growing mechanism, and the corresponding formula for the effective threshold to be used. And in this diagram we see the comparison of such determined theoretically effective mode 2 thresholds with the experimentally measured ones, and we see a good agreement for various metallic materials. The experimental values are always a little bit higher because the cracks are not perfect and they are not absolutely closure free. Okay, so this analysis we done for mode 2, we also wanted to apply for mode 3 cracks, which is a more difficult problem, and we started with the easier case of in-plane crack propagation, so for the BCC metals. And in this case, the crack propagates under local mode 2 according to this mechanism. At the locally serrated crack front, the crack advances under local mode 2. So what we need to do here is to determine local mode 2 stress intensity factors for such inclined crack fronts. And here is an example of fracture surface from the SEM in this central area. This is the crack propagation under a remote mode 3 loading. And we can see here also the lines we saw at the previous image, but they are highly inclined with respect to the pre-crack front. And it shows that actually the mode 3 loaded crack propagates locally at this direction of these fibrous patterns. And for example, in this case, the crack initiated and grew in the segment A in this direction, and then continued into segment B, which is another grade with a differently oriented slip system. And in this case, in this segment B, the crack grew upwards in the 3rd dimension. And meanwhile, in another place, the crack grew in the segment C in this direction, and then they met at different heights. So they need to be connected by creating such a step observed here. So it confirms the model of local mode 2 crack growth mechanism. And for the calculations of local mode 2 stress intensity factor, we modeled this specimen, which was used in experiment, loaded by torsion or by simple shear in order to obtain mode 3 crack loading. And here in the FEM model, it has 2 levels of submodeling in order to refine the mesh approaching the crack tip and to get also good convergence. And here, this is the crack front we modeled, so we have such a sawtooth shape with a certain angle of the asperities. And we modeled it with different angles of the asperities so that we could follow the dependence on this angle. And we evaluated the local mode 2 stress intensity factors along this line at these nodes. At the corner nodes, it's not well defined, so between the nodes 2 and 8, we evaluated the local mode 2 stress intensity factors, which are here in this graph normalized to the global mode 3 stress intensity factor, which would be valid for a straight crack front in the same specimen and loading. And we can see that already for an angle of 40 degrees, we obtain the ratio of 1, which means that the local mode 2 stress intensity factor is as high as would be the mode 3 stress intensity factor for a straight crack. This is quite high component. And in this diagram we see the dependence of the local mode 2 stress intensity factor on the angle of the asperity. And from this dependence we can analyze the experimental case. So if we have a specimen that we load under global mode 3 at threshold. So we have the mode 3 effective threshold that we measured. And if we have the local mode 2 mechanism operating, then this relation should be valid. So it means that the ratio of the local mode 2 stress intensity factor to the global mode 3 stress intensity factor should be equal to the ratio of the experimental measured mode 2 effective threshold and mode 3 effective threshold for the same material. And here at this diagram, this is also the dependence on the angle, but it is evaluated for two materials, for niobium and Amco iron. And here the horizontal lines represent the experimental ratio of the mode 2 and mode 3 effective thresholds. So in this case, when they meet the dependence on the angle, they show us that in this area between 25 and 30 degrees should be the averaged angle of the asperities on the pre-crack front. So it means that the local mode 2 mechanism is possible to operate for already relatively small angles, 25 to 30 degrees. And of course we were interested in such an angle on real pre-crack fronts. So these are new preliminary results. We looked at the pre-crack and we draw such a segmented line and express the ratio of the length of this segmented line to the projected length, which is the linear roughness. And this value gives us the averaged angle of the inclination of these lines. So this is the angle we are interested in, and for niobium and Amco iron it is somewhere about 25-26 degrees, which is in a quite good agreement with what we expected from the previous analysis. So it means that the results are very promising in terms of possibility of formulation of a quantitative formula for mode 3 effective thresholds in these materials. And that brings me to the conclusion. So we investigated mode 3 crack propagation in BCC metals which grow by local mode 2 mechanisms, and for the serrated crack front we evaluated local mode 2 stress intensity factor components. So we found that relatively high local mode 2 components is present on the asperities implied by 25 to 30 degrees, and the results were in agreement with the experimental measured ratio of mode 2 and mode 3 effective thresholds. So this is what we want to do next, to formulate a predictive relationship for effective mode 3 threshold in the BCC metals. So I'd like to acknowledge the cooperation with our colleagues from Austria, from Elching Institute and Montan Universität in Leoben, and thank you for your attention.